How to decide maximum allowable nozzle loads? Is this question bothering you? Let us discuss that in detail. Welcome to our Static Equipment Design channel. We provide professional training in static equipment design. Courses offered: Master, Pressure Vessel Design, as per ASME Section 8 Division 1. Master, Tall Cylindrical Tower, or Column Design. Master, Heat Exchanger Design, and TEMA Requirement. Master, PVElite Software. Master, Storage Tank Design, as per API 650. To learn more, register with Learn More link in the description, and apply coupon code MASTER15 to get amazing offer.
Question is how to find the maximum allowable nozzle loads which can be allowed on our vessel. Okay, so first of all, to understand what is the maximum load which can be allowed, we need to understand how these loads are coming. Okay, so to understand that, let us consider a simple pressure vessel. It's a vertical shell, and a nozzle is connected to the shell, and with that nozzle some piping is connected. Okay, now these piping will exert load on the nozzle depending upon how they are rested, whether the support is provided here or there are bellows attached. Because if the bellows are not attached and the pipe is quite long, then due to thermal expansion, lots of loads will be transferred to the nozzle. Okay, so finally the nozzle loads are coming from where? Nozzle loads are coming because the piping is attached to the nozzle. Okay, and depending upon the configuration how that pipe is attached, the final nozzle's load will be derived from that. So the procedure should be such that when all the piping layout is done in the plant, finally the stress analysis of the pipe will be performed depending upon how the pipe is supported, what is the length of pipe, what is the thermal expansion, whether bellows are provided or not. So depending upon that, when final stress analysis is done by the piping engineer, we get the final load which will be acting on the nozzle. So normal sequence is to do the stress analysis and then we get the nozzle loads. Okay, but normally that does not happen during the typical life cycle of the project. The stress analysis is done at very last. Okay, when we have all the piping layouts done, no change, at the final stage, the Caesar stress analysis is performed. So if we decide the nozzle load at that time, it will be too late to finalize the vessel. Okay, so if we want to, normally we have to do it beforehand. Okay, so that is the reason it comes that we have to find out the nozzle loading which is applicable, that maximum nozzle loading which is allowable for this nozzle beforehand, before getting the data from piping. Okay, so now if we go further, so there are two reasons why we need to find this maximum allowable nozzle load. First is we have to complete the vessel design, because we cannot wait for the nozzle loads coming from piping. So we have to complete it and give it to the vessel fabricator so that he can perform the final fabrication. Okay, now the final loading which we have decided, which we are calling it as a maximum allowable nozzle load, that we give to the piping department. Okay, that is the second output which we give. Now it is going in reverse manner. Actually they should give, but now we are giving them that this is the maximum load which we have considered for that nozzle. Now whatever Caesar or stress analysis you are doing, you have to make sure that the piping load does not exceed the value which we have given. Okay, because that is the load for which that calculation has been done. So that fabrication also might have started. by the time they arrive at the actual value. Okay, so they have to provide supports, provide bellows, and design that piping such that their final load exerted on the nozzle is lower than the value which we have given. Okay, so now again the question remains, then how to find, if we have to find the nozzle allowable loads, how we can do that? Okay, typically we get client specification which will have the maximum allowable nozzle loads already mentioned based on the size of the nozzle and the flange rating. These are the two criteria. Based on that, some nozzle allowable loads, maximum allowable loads on the nozzle are given in the specification. Okay, whether that might be available, or we can follow some standards like EIL standards. Okay, where again with the same nozzle size and the flange rating basis, the maximum allowable nozzle loads are already provided to us. But please remember, these are uh, not actual loads. They are just we have taken some load based on some reference. Now we'll come back to that, how this EIL standard or client specification mention these loads. We'll come back and see that how that is calculated. But these are typical. These are not the final loads. These are just arbitrary load given. Okay, so that we have some data to go ahead. Okay, now let us see how these loads, if we have to calculate, if there is no EL standard available or we don't have to follow that, the client specification does not mention about the maximum allowable load on the nozzle, then how we will do that? Okay, so there the Dennis Moss book comes into the picture, and that is the book which you can follow to calculate this 3 loads which are given by this Dennis Moss book. Okay, and these loads are longitudinal bending moment that can be calculated directly by using this formula. Now here the D is the nozzle diameter. Okay, and 110 is a value, beta is a factor, and this beta depends upon the flange rating. You can see here, based on the flange rating, that B value also will be available to us. So once we know the size of the nozzle, we can easily calculate the longitudinal bending moment. Okay, similarly, circumferential bending moment also can be calculated. Same formula, only that constant value is little changed. We can calculate the maximum circumferential bending moment for that size of nozzle and rating. Okay, so we have 2 values. Radial load also can be calculated by using that factor of B and multiplying with 500 and D. These are the values in foot pound. Okay, whatever unit you are doing the calculation, you can convert it from here. Okay, so these are the 3 loads. Now you will see that there are other loads, the torsion also, which is applicable. Okay, but torsion is not does not affect the stress value to a great extent. Okay, and that is the reason those values are ignored. We have not considered those values. Okay, so because finally that shear and torsion effects are negligible in the final stress outcome. Okay, so we can eliminate them. These are the major loads which we have to deal with. Okay? So once we have calculated these loads, the next activity will be to take these loads and do the calculation in PVElite. PVElite, we can go to WRC. We'll see what is the procedure for doing that calculation. We will see that. So now we have these 3 loads. Okay, now please remember here one more point. These loads are for process nozzles which are connected to piping. So typically the manways and the inspection nozzles, those are eliminated. Those are not considered for maximum allowable nozzle load. We don't consider any load coming on the manways or the inspection nozzle, only for the process nozzles. Okay, so that is the second point to be remember. And the third point to remember is that for nozzles which are coming on the formed heads, either elliptical, toruspherical, or hemispherical, if the nozzle is coming on that, then you have to compare, you have to calculate the resultant of these loads by, you have to calculate the resultant bending moment by adding these two values with a square root. Okay, do the square ml square plus m5 square and then under root. That will give the resultant of these two bending moments, and with that resultant we have to compare the final stress which is coming on that nozzles which are on formed heads. Okay, so for cylindrical, the nozzle loads coming on the cylindrical shell, there is no change. But for the nozzle load nozzles which are coming on the formed heads, the calculation is little different. Okay, so that is all. That is how we calculate maximum allowable nozzle load. Hope it is clear to you. Now we'll see how we do this calculation in PVElite. Okay, making sense? Let us see that.
Yep.
Now you can see, right?
Yes,
Yes.
sir.
Yeah, great. So I've just modeled one vessel. I thought you guys are able to see it. No problem. Just I have added one cylinder and I was adding that nozzle, and just keep that nozzle elevation so that we can. Cylinder length is 3000, so I'll take 1500. Okay, now I have added that nozzle. Okay, if I have to do WRC calculation, I'll go in this. Now which WRC to be performed, 107 or 297?
So 297.
297. Are you getting it, Pandian? Why 297? Why not?
No, Abhishek, honestly, no.
Yeah, I think you will be not gone to that section till now.
No, not yet. Yeah.
Yeah, and so we have covered that WRC and 297, but basically 297 gives the stresses in both the nozzle also and the shell also.
Okay.
Okay, 107 will give you only stresses in shell. It will not give you the stresses in nozzle. There are lots of parameters, but I'm just telling you one why we are selecting here 297. The main reason is we'll get stresses in both, because we have to qualify nozzle as well as shell. Okay, we cannot just qualify shell and say that we have calculated the stresses. So 297 is what you have to select for cylinder to cylinder. The limitation for 297 is that is only applicable for cylinder to cylinder. If there is a mother shape, you cannot apply that. Okay, but here we have cylinder to cylinder, so we can definitely apply. Now if you go see here, there's lots of standards available. Okay, like that you can, if you have some specification which you are following, you can inbuilt in PVElite itself, and if you just select that, the loadings will be already taken from that. Making sense? If you don't have any specification and you want to just randomly put some values, so due to thermal expansion, which force will be more prominent? If the piping which is attached, again you see thermal expansion may be a problematic for you. So which force here in all these forces and moments, which one will govern more for thermal? Any idea?
It
So
should be
radial
P.
force. So radial force.
Yeah, radial force P. Okay, because see, mostly the thermal expansion will be always linear. Okay, so it is going to affect your radial force. So if you feel that the radial expansion is going to be governing, okay, but before the project is finalized, that is also difficult to predict. Okay, only basis you can say that if the temperature is very high, you can imagine that that because of this temperature, your thermal or linear expansion may be more. So considering that, you can evaluate. But finally, the length of that pipe, that is going to be the governing criteria for this force. If there is a bend in pipe, okay, immediate bend in pipe just after nozzle connection, then also the force goes down. Okay, because that bend will be able to take care of that thermal expansion. That is the reason always, if you see, whenever that vessel is connected with a pipe, immediately after they will provide some bend. Okay, so that way you control the thermal expansion. Making sense?
Yes, Abhishek, you are correct.
Yeah. So now you can put all the values which you want here and randomly, and then try, for which value it is failing, which value, if you can see the effect of all of the loadings also. So 5,000 will be very less load for this. So I'll just take 50,000. See, now if I say 50,000, your vessel at pad edge, that is failing. Okay. Can you imagine which location it is? Vessel at pad edge.
Sir, I have one question, sir.
RF pad location, it means, correct? Vessel at pad is means.
Vessel at pad edge means?
RF pad location.
So whether the stress is in RF pad or shell?
RF pad extreme into cell, that junction.
See, if there is a pad here, okay.
Yep.
So finally that WRC gives the stresses in shell or nozzle. So this is the stress which is getting generated here, at least this location where the pad is ending.
Yeah, correct.
Correct.
That's what I meant.
So the stress, yeah, so that is correct. So it is stress at now. If you have to, reduce this stress, what can you do? If you don't have that option to reduce this load, but you want to minimize this, is there anything you can do?
Increase RF pad thickness.
Sorry?
Increase thickness.
Increase the
Thickness.
Yeah, he's saying increase the RF pad thickness.
So whether increasing the RF pad thickness will help? See, that stress is not in RF pad. It is in
Shell only.
shell. So
Sir,
if
increasing cell thickness.
Shell in thickness.
shell thickness will definitely help, but you'll not like to do that because that will be too much cost implication for that.
Nozzle thickness.
Okay,
Whether we'll
Sir,
have-
Increase RF pad diameter.
Sir,
Sorry?
Increase RF pad diameter.
One by one. Adnan, you are saying something?
We increase RF pad diameter.
Yes, that's very correct. So see, finally, what is happening? Why this load is the stress is governing? That might be reason that finally there is a lower area which is taking care of this radial load. So one thing is we can increase the diameter, okay, of this pad. Okay, that will work only when you have within the limit of your reinforcement. Beyond that, will not have much effect. So let us increase that. Definitely, we may not completely eliminate it, but some advantage we may be able to get. See, from 1.7, it is down to 1.4. Okay. Now, if I
Sir, how these stresses are coming because of the pad?
how the stresses are coming because of pad means?
How this is related to pad dimensions?
See, because pad is also providing stiffening, right? That thickness till that location is more.
Okay, sir.
Where your pad is providing that stability to that load, that factor is also considered in WRC.
Okay, so the WRC considering pad dimension as
Pad
well as
dimension also.
shell dimension.
Yeah, because we finally that if some moment is getting created due to that load, that it will be affecting at the pad OD. The shell stresses will be more where your pad is, till what your pad diameter is there. Now let us see if I increase the thickness. Let us see if any implication is there. So from 8 mm, let us make it 16 mm. We are increasing more so that we can see some visible, values change. anything is happening. Okay. So now if I have increased the T, even if I change that to double, no change in the stresses. Okay. Now let us say I increase that OD further, make it 200. Now it is 1. Okay. If I make it 250, see, by increasing that pad diameter, I have controlled that stress at OD.
So if we provide the stiffener gussets,
See, gusset you can provide, but that calculation you have to do that in FEA because that
Okay.
configuration cannot be considered by WRC.
okay.
So WRC just take care of this diameter factor because that is affecting your opening size. Okay. So
Yeah, Abhishek, that is a point. Like, still gussets. In which condition they are providing those gussets?
yeah.
Once we are on
Yeah, we can discuss that also. So now the next question is that for which nozzles you provide gussets, right? That is what you are asking. Pandian, is that rightly? I'm asking the question. Yeah.
Yes, Abhishek, you are correct.
Yeah, correct. So you might have seen that gussets only for smaller size nozzles, normally for 2-inch or very rarely for 3-inch. Mainly for 2-inch, you'll see gussets, or we call it as stiffeners attached to that nozzle. What do you think may be the reason for that? Why
You
for
said nozzle section very less to withstand the bending. It's a cantilever condition, no?
correct? So what happens? See, when your nozzle size is small, so your schedule, even increase in schedule, your thickness will be very small compared to when you have larger diameter. Okay. And when you have smaller size, smaller thickness, your section is weaker. So if something is hitting your nozzle, okay, maybe during transportation or installation, it may immediately break. Okay. It will be very weak. So just to strengthen that smaller nozzles, 2-inch, which are very fragile, we provide stiffeners. Okay, 90-degree apart, 2 stiffeners. That is the standard. So if you want to avoid this, many times client will say that it does not look good. Okay, when you provide stiffeners, it is not suiting that appearance of that vessel. So what you do to avoid stiffener, if you don't have to provide, then what you will do? You go for long well neck nozzles. So long well nozzles are LWNRF, you might have heard of, right? Have you heard of that?
No, Abhishek.
Not heard of. So
No,
for
not
2-inch or 3-inch, we select LWNRF nozzles. So that is like that nozzles comes with flange attached to it. Okay, and the thickness is more because that is made from forging. So you have larger thickness and your flange is already attached to it. You don't have to do any welding. I'll just show you a picture of it so that you can visualize. So these are long weld neck. So your neck will be larger and it will be thicker. So they are more stronger than your normal 2-inch pipe. So we prefer that if we have to avoid stiffeners for the nozzle. Making sense, Pandian?
Yes, Abhishek. Yeah.
Yeah. So only for 2-inch nozzles, for your specific question, that when we provide stiffener, mainly for 2-inch, very rarely for 3-inch. If you have very smaller thickness and you feel that it may be very fragile, for that you can provide. Otherwise, you only for 2-inch nozzles, you provide always stiffeners. If you want to avoid that, you have to go for long weld neck. If you're selecting long weld neck, you don't have to provide stiffeners.
First we shall go for with the stiffener because the long one is costly.
Yes, that is the part. So unless client will demand, fabricator will not provide that because they cannot accept any cost increase. Okay.
Hope you liked the content. Subscribe the channel to get access to lots of such content. If you want to purchase the full course, go to the link in the description and register.